Okay. This is correct.
Okay. So, my name is Alex. I'm a grad student up at UNH, working with Todd Gerdot, and we are working on aquaculture and aquaponics. The extended title on my slide is Developing a Sustainable Northeast Aquaculture Industry Using Aquaponics, a Waste to Resources Approach. So, why aquaculture? We use aquaculture because aquaculture accounts for more than 50% of the total seafood production worldwide. The annual industry is growing at a rate of 6% every single year, while the global fisheries are declining at a rate closer to 12 or 13%. 80% of the seafood that we eat here in the US is already imported, so we need to figure out a way to reduce that necessity, and we can do that through aquaculture. That leads to an $11 billion deficit in trade. So what we're using is recirculating aquaculture systems, meaning that we reuse our water. From our research, you can recycle water up to 99%, and our research suggests that we're running our systems right around 95% reuse right now, so we're wasting about 70 gallons per system per day. We mechanically remove all our biosolids, and that waste is what we're most interested in, as well as the solubilized nutrients in the water. And our biofilter converts and removes the nutrients that would be toxic to fish and that are excreted by fish into a more usable form by plants. So here's just a little diagram of what our basic system would look like. We have a fish culture tank, mechanical filtration, where the solids get removed, biological filtration, where all the hazardous nitrogen products are converted to nitrate for plants. And then we have aeration and oxygenation because that's necessary for the fish and the bacteria that grow in our systems. So we're most interested in this little yellow dot here in the bottom, the sludge. Right now it's an expensive byproduct as part of the aquaculture regime, and most people either have to pay to have it hauled off or they send it out to a settling pond and wait for it to break down, leads to eutrophication, algae ponds, things like that. So, hydroponics. This is growing plants without soil, and we are using a deep water culture, meaning that we use rafts over about 10 to 12 inches of water depth. And this is efficient because we're using 90% less water to grow up to 4 times the amount of plants per square meter. One advantage is that there are commercially available nutrient solutions, and these are even tailored specifically to plant varieties or just generally species. What we're doing is combining these two, aquaculture and hydroponics, to make recirculating aquaponic systems. So now we're reusing all our water at 95%. We can grow plants at 4 times the growing area, and again, there's still commercially available fertilizers that you can add into aquaponic systems that are fish safe and plant safe. But the challenges are that the optimization of the water quality is quite different. Fish prefer a pH right around 7, plants obviously a lot lower than that. Alkalinity plays into that, and so does temperature and other things like that. So what is going to be the efficiency of our fertilizer, both soluble and insoluble? So the objectives of our research are to balance nutrient production and uptake in aquaponic systems. My job is to characterize the nutrient production from aquaculture. So my systems literally only look at the aquaculture side, and then the following research after this is going to focus on integrating the two systems and really looking at the specific plant uptake and fish production. So we're looking at 13 different macro and micronutrients. And also, we're trying to develop a naturally derived nutrient source from aquaculture that we can compare to the commercially available hydroponic fertilizers. So for the experimental design, we have 3 identical systems. They're 1,300 gallons total. We're using a moving bed bioreactor biofilter, and that's where all of our bacteria are housed. They convert ammonia to nitrite and nitrite to nitrate Ammonia and nitrite are both toxic forms of nitrogen to fish, so it's really important that we keep that in there. And we're using drum screen filters, which tend to be on the expensive side, but they're the most efficient way to remove the biosolids from the systems. And we're running 40 micron screens, so we're really filtering out all the solids really down to a really fine level. The fish tanks are right around 450 gallons each. The first trial was done with Nile tilapia. The current trial I'm running right now, we're using rainbow trout so we can get more of a native species in here. And we're running about 100 fish per tank because we stock them at an expected harvest density of 0.33 pounds per gallon. We chose that number because that is the maximum oxygen demand that we can meet by injecting air via a regenerative blower outside of our building. If we were to use liquid oxygen like we do for our quarantine system, we can bring that number up to about 2 pounds per gallon of fish production. The diets that we're using for the tilapia is about a 40% protein feed, pretty standard across aquaculture industry, and we use a 24/7 feeding and lighting cycle. Now for the trout, they need a higher protein because they are a carnivorous fish versus the omnivore like a tilapia. So we're running that diet that we're using for them is right around 45 to 48% protein. So there's definitely a lot more. Just looking at the water clarity, you can already see that there's a big difference on the solubilized nutrients. And so here's just a few pictures. The overall system, our drum filter over on the left, and then some of our biofilter media. It's just a plastic wagon wheel looking media. So a few of the measurements we're looking at are the fish growth, including their average weight, their food conversion ratio, because we're really trying to run these systems like a commercial production facility. We're trying to quantify how much a commercial farm would produce nutrient-wise. We look at water usage and the nutrient chemistry. We are quantifying everything that goes into these systems and everything that comes out. So it's really important to try to manage these at what we define as a pseudo-steady state. If anybody has ever worked with aquaculture at all, it's a hardly steady state. So it's really difficult to try to maintain these systems, especially 3 independent systems with water usage and how much food the fish get, because there's so many different factors that go into this. So what we're doing is, overall, how do we get fish feed to become plant fertilizer? We're doing a nutrient mass balance, like I just said. We're quantifying everything that goes into the system, including water and feed are the 2 main things that get added. We also add sodium bicarbonate because that is what commercial fish growers use to buffer the pH and alkalinity. Now, for all you plant people out there, you hear sodium, I'm sure you guys are ready to run out. But I promise you that in aquaponics, we can change that because we will use potassium bicarbonate in order to bring the potassium levels up in the solubilized solution and not have all that sodium in there. So some of the considerations for plant nutrient availability. The water quality parameters are really important. The pH especially, alkalinity can affect that, temperature. And what I'm talking about here is chemical speciation. For example, iron 2 versus iron 3. When the pH is too high, iron becomes an insoluble form, can no longer be taken up by plants, and is therefore not usable and basically equivalent to a rusty pipe in the bottom of your tank. When you keep the pH below 7, ideally 6.5 or less, that iron remains in an iron 2+ form, and then you can have full bioavailability to the plants. Another tough part about doing this with aquaponics is that we're trying to maintain a stable and consistent nutrient supply. Fish grow at an exponential rate at the beginning of their life, so you can feed them upwards of 20% of their body weight per day. That's extremely high, whereas when they get to a subadult stage, you actually back them off to about 3, most likely 2% body weight feed per day. So the actual amount of nutrients in the solution is quite different across the growth cycle. So the way that we would counteract this is to have different ages of fish all growing at the same time. So we would have a constant supply of fish to be harvested every week or every bi-weekly. And then we will also have a stable nutrient supply because that biomass would always be the same and the amount of feed going into the system would be the same as well. So in order to find out what these levels are of the metals in solution, we're using ICP-OES. It's just a super long acronym for Inductively Coupled Plasma Optical Emission Spectrometry. Okay. And so what we're evaluating there is the process streams, the fish, the feed, the plants when we get to the aquaponics side of things or hydroponics side of things. And I have some preliminary results to share with you guys. So I threw up two commercially available nutrient solutions that are commonly used. And this is specifically for lettuce because lettuce is the easiest to grow, takes about 28 days, and we're trying to speed it up as much as we can. In the background, you can see one of our aquaponics systems. We've done some preliminary studies on those, trying to get lettuce growing with harvesting about 200 heads of lettuce every single week. So what you can see here is that our culture water and our wastewater is actually severely deficient in many of the different nutrients. So a few of the macros and most of the micronutrients are few and far between when it comes to our solubilized nutrients. Now what you don't see here is the solids analysis because we're just getting those results back, and it's actually interesting because our nitrogen and what was the other one? Nitrogen, macro. There was another macro that was meeting enough of a supply. So even with these deficiencies in our systems, we had amazing growth with our first trial of lettuce and fish in that coupled system. So even with these deficiencies, why are we getting this amazing growth? That's what we're trying to find out. Basically, it's been a black box for people, and that's why we're doing this research. What I was saying about the solids is that what you don't see is that all the deficiencies that you see here are mostly made up in the solids, meaning that it would be a good idea for us to try to liberate those nutrients because a lot of those are locked away in the solids. So we have an engineering student that's coming in right now, and they're going to be working on aerobic and anaerobic digestion of these solids and trying to figure out what sort of efficiency we can get at removing and liberating these nutrients from the solids. So right now we're meeting plenty of nitrogen demand. So that's definitely an easy part. Interesting, phosphorus was split about 50-50 between the culture water and the solids. And the culture water is literally, just to define this for you guys, the culture water is literally the water that's in with the fish. And the wastewater is actually that same culture water that is used in the backwash to remove the solids. So it sprays maybe about 1 or 2 gallons every 15 to 20 minutes out of the system until we reach that about 70-gallon water usage per day. So that's why those two streams look fairly similar. And here's one of our plants that we harvested. So what are the implications of this research? You have improved economics. You've basically taken an expensive waste stream and you're monetizing it. You're reducing your environmental impact. Now, point source pollution from aquaculture is a big deal, and the excess phosphorus runoff really leads to eutrophication in natural waters, so we can prevent that. There's a ton of modular innovation opportunities because you see these systems popping up all over. Now there's small systems that you can keep in your kitchens for hydroponics and aquaponics now as well. So you can keep a hydroponic system above your fish tank and grow your greens and microgreens for your kitchen. And it really builds on consumer preferences. It's highly efficient, it's locally produced. People can come out to your farm and visit and pick up their fish, and you can have the fresh, like extremely fresh fish the same day. So our next steps, like I said, we're working on rainbow trout right now. So we have them stocked out about the same density. Also, just forcing air into the water, not using oxygen. And then, like I said, nutrient liberation, aerobic versus anaerobic digestion. And we're currently building out 3 experimental replicate greenhouses that we can completely control, complete with electricity monitoring, gas meters, things like that, so we can actually get an economic model built around the production of these types of systems. So I will field any questions if you guys have any. Yago?
Yeah, thank you. Actually, your very last sentence was a question that I wanted to ask you about. In your title, you're talking about a sustainable production system, but you really didn't talk about energy or heat or any of the things that in my mind have always been the thing undermining this sort of system at any scale. I guess
Definitely.
that's like your first, well, I guess when you say a sustainable system, but not really talking about those other things, I guess what you sort of mean by that and what you think the prospect is. What's those other things come into the equation?
So in the Northeast, it's especially difficult because of our winters. Our harsh climates, really, especially for heat. Heat is very expensive, but when it comes down to it, the pumps, the cost to move the water around is actually one of the highest. So electricity ends up being our highest cost. In the Northeast, you tack on heat in the winter, and then that really pushes your profitability way down. That's why we're trying to move towards rainbow trout, because they're a cold water species as well as a carnivore. And so by doing so, I've actually taken my whole building temperature and reduced it down so it's maybe 5 to 10 degrees above ambient temperature outside. So I have to wear a coat in order to feed my fish, but we're definitely paying a lot less for that heat demand now. So there is an opportunity, and there are local fish hatcheries and things like that are run outside with streams flowing through them. And you could definitely do that with trout and then literally divert that stream and probably set up a hydroponic system as part of that, or divert the stream in there, and then as the nutrients are removed, replace that water back into the river. So there's definitely opportunities like that. If you go further south, there's outdoor facilities everywhere. A lot of people trying to do aquaponics and hydroponics just in raised beds, basically. So yeah. Anita?
So you, feeding fish, what's the protein source you're feeding the fish?
So the protein source is fish. Most of the fish feed right now comes from other fish meal-based diets. And so that's basically ocean bycatch, which is another issue altogether. We could do a whole talk on that. But some of my previous research, I spent a few years up at Dartmouth doing some sustainable feed research up there. And we were replacing fish meal and fish oil with marine microalgae. And that showed extremely promising results. But again, we come back to the economic model, and that's where the contentions lie. So, anyone else?
I think we're all looking forward to seeing the 3 new greenhouses up and running, but
Yeah.
I know.
We'll probably have fish in there within the next few weeks. So we're getting our first fish systems up and running. So.
And you're going to run the fish out in Kingman, or are they farm building, or?
Both. So right now I have the fish for the 3 greenhouses, and they've been here for about a month. They're growing quicker than I can keep up with them. They're actually skipping. We have a feed calculator we use, and they've skipped an entire week because they're growing so quickly. So Todd has actually asked me to slow them down. So we got to lower the temperature and hold back a little bit of feed just to get them on our schedule. So. Okay, thank you.